So good morning, everyone. So first of all, I would like to thank Gediminas and all the organizers for setting up this fantastic meeting. So today, I will talk about probably the most famous model describing a multi-component system, and obviously, I'm talking about the Fermi-Haber model. So as you know, this Hamiltonian is very popular, especially in 2D, as it is believed that it hosts high TC superconductivity. But there the situation is not completely clear, as all the numerical approaches are deeply affected by limitations, and in addition, experiments need to lower the temperature, quite a lot, in order to observe superconductivity. And because of that, so in my talk, I will focus on 1D physics, okay, where at least we have full control on the numerics. So all the results that I will show you have been obtained thanks to tensor networks implementations. Okay, so as we heard yesterday already, this is the 1D Fermi-Haber model. So this T describes the tunneling processes of up and down fermions between nearest neighbor sites, and this U term is the interaction. So here the phase diagram is super well known. Let me just remind you what we can find. So if you are at half filling, so density 1, as soon as the interaction is repulsive, so we have a Mott insulator, so with exactly one particle per site. And this phase is an insulator. Why? Because the charge degrees of freedom are gapped. Okay, there is a finite charge gap delta C. But in addition to that, so what I can tell you is that since we are considering a spin-full fermionic system, so we also have to consider the spin degrees of freedom. And here, the spin gap is 0. So there are gapless spin excitations. So in order to have a finite spin gap, so there are two different configurations. So in one configuration, we can have some fermionic pairing, on-site or non-local, or we can have some magnetic ordering, And the fact that here we don't have magnetic ordering can be properly understood by working in the perturbative regime. So in particular, when the on-site interaction is much, much larger than the tunneling amplitude. So, and in particular, in this regime, you can simplify this Hamiltonian by following some standard procedure. So in particular, we can project this Hamiltonian into the subspace with no double occupancy. And then we can expand this Hamiltonian up to the second order. And if you do that, so we end up with a very famous isotropic Heisenberg model. So where these S are now effective spin 1/2 operators. So there are two important things that I have to remark. So in particular, this J, the effective spin-spin interaction emerges perturbatively. And because of that, you can see that this J is much, much smaller than T, than the tunneling amplitude. And in addition to that, this interaction is isotropic, so which means that the SU2 spin rotational symmetry is preserved. And because of the Mermin-Wagner theorem, so we know that at least in 1D, at any temperature, this symmetry cannot be spontaneously broken. So this basically excludes the possibility to have some magnetic ordering. In order to, for example, give rise to a finite spin gap, so what we can do is to explicitly break the site inversion symmetry. So site inversion symmetry basically means that we should have some effective lattice dimerization. And if you do that, so especially in this strongly repulsive regime, we end up with a topological insulator. Okay, this has been done, for example, in the group of Immanuel Bloch, where they have these two legs Hamiltonian, and they do break the site inversion symmetry by considering spin-spin coupling along the diagonal and the vertical direction. So since here the distance is different, so you explicitly break this site inversion symmetry. Or another strategy has been implemented by Conrad and Tillman at ETH, where they, for example, had an additional optical lattice, so they have a super optical lattice, so that they can engineer an effective tunneling, staggered tunneling, if you want, and you end up with a kind of SSH physics that we heard yesterday. Good, but what I want to remark is that within this Fermi-Haber realization, so the topological phases that you can have are topological insulators. Okay, there is no particle motion. Good, so the situation is completely different if we work in a regime where now the density is smaller than 1, okay, but still in the perturbative regime. So of course now, so if we remove particles, so we can try to follow the same procedure as before. So in particular, projecting this Hamiltonian into the same subspace with non-double occupancies, expand everything, and we end up with the equally famous isotropic TJ model. So you can see that again, there is the emergence, perturbatively of course, of this effective SU2 symmetric spin-spin interaction. But in addition to that, since there are empty sites, so now particles can move, so we also have to consider tunneling processes. Crucially, so you can see here, these two guys, these are the projectors. So these are the guys allowing you to exclude the formation of double occupancy, okay? So the two important features here that I want to remark is that, again, no double occupancy and very, very small effective spin-spin interaction, okay? And isotropic. Now, the thing is the following. If the particles can move, you know, the ground state of this Hamiltonian does not describe anymore an insulating state, of course. So that's why the charge gap here is 0. So, but here we cannot exclude a priori the emergence of some fermionic pairing. So fermionic pairing, you know, can be related in some cases to superconductivity, you know, but one has to be very, very careful when talking about superconductivity in 1D, okay? Again, so we know that unless we explicitly break the U1 gauge symmetry as in BCS, we cannot have long-range order of superconducting correlation functions, but still we can define a one-dimensional superconductor, kind of, if we have that all the correlation functions related to superconductivity, I will show you example on that in a few slides, decay algebraically, and at least one of these correlators is the one decaying to 0 much slower with respect to all the other correlation functions. And okay, so in order to see whether here we can have superconductivity, we can do some DMRG. And these are the results obtained, you know, 15 years ago, so as a function of density and J over T. And you can see that yes, so in particular here in this region, so we can have one-dimensional effective superconductivity. But there is one important thing that probably you already noticed, that in order to have superconductivity, J has to be at least, you know, it has to be larger than T. So J over T has to be at least 2. And of course, this is a completely unrealistic scenario, because as we have seen, so J is always much smaller than T. So which means that for alkali atoms, that they can basically engineer this Hamiltonian, so having one-dimensional superconductivity is completely out of reach. It's completely unrealistic, okay? Now, in order to kind of try to overcome these limitations, so people in our community started to think about different platforms where, you know, we can go beyond this TJ description. So there have been a couple of fantastic experiments. So the first one has been performed at GILA, where they use polar molecules in order to polar molecules into rotational states in order to have a mapping between rotational state and spin up and spin down particles, or in the group of Antoine Brouet, where they used a 3-level Rydberg setup. Okay, so here the nice thing is that, you know, the spin couplings are completely anisotropic. So the SU2 symmetry is explicitly broken. So in principle, we can have magnetism. And in addition to that, so the spin-spin interactions are completely decoupled from the tunneling amplitude, and they can be very, very large, especially in polar molecules. So, and good, because in this way, in principle, so we can have, you know, 1D superconductivity, and I can also tell you that, you know, years ago, we also realized that we can have some kind of topology in this kind of setup. But there are two important things. You know, working with polar molecules and Rydberg atoms, especially at ultra-low temperature, is not easy at all. You know, having, you know, polar molecules at equilibrium, more or less ground state physics is tough, I would say. But the important thing that I want to remark is the following. So here, the on-site interaction in the best case scenario is basically infinite. You know, in polar molecules can also be, you know, you can also have two-body recombinations, which are, you know, a huge problem, and so on and so forth. But here, on-site interaction is basically infinite. You cannot have two Rydberg excitations on the same site, and you cannot have two polar molecules in the same site. So, and here comes our proposal. So here, we would like to engineer a kind of TJ Hamiltonian by using fermionic magnetic atoms. So as we heard yesterday in Sylvain's talk, so these magnetic atoms allows one to engineer higher spin models. So for example, with erbium, we have an effective 19-half spin system, and with dysprosium, we have an effective 21-half spin model. So, and if we trap one of these atomic species in a 1D optical lattice, this is a Hamiltonian that we have, where of course there is tunneling, so there is hopping as usual. And crucially, the dipolar interaction gives rise to this effective spin-spin interaction. So where there is an Ising term and there is a spin flip coupling. Good. Now, the thing is the following. So you can see that here there is U, the on-site interaction. And you know, magnetic atoms share an important property with alkali atoms. So in particular, it is possible to have Feshbach resonances. flashback resonances, you can see that the on-site interaction depends on the S-wave scattering length that can be tuned through flashback resonances, and depends on on-site interaction, on the on-site contribute coming from the dipolar interaction. So basically, by changing the scattering length, we can reach all the regimes of on-site interaction that we want, okay, in principle. This is not certainly easy. Good, so, okay, we have tunability of U, we have T, but we still have, for example, a Nightingale spin chain. That if you want to relate our physics with the one that you can get in Fermi-Hubbard physics, this higher spin model is completely useless. But in experiments, it's possible to use off-resonant light in order to isolate the dynamic of the system between these two MF states. So which means that now these spin 1/2 operators can be replaced by effective spin 1/2 operators. Good, and the important thing is that if you now plug these values, so F and MF, into this expression for gamma, so you see that gamma enters only in the spin flip processes. And if you do this simple algebra, you see that now J-perp is much, much larger than JZ. So again, the SU2 symmetry here is explicitly broken, and this is a good point. But now, okay, we have tunability of U, we have T, we have effective spin-spin interaction, but we would like to see whether this spin-spin interaction is large enough, to give rise to new phases. And the answer is yes, so you can also check some experimental results obtained by the group of Markus Greiner. These are our calculations for this lattice spacing, which is short, but not crazy short. It's not even a UV lattice with this number. And you can see that J-perp strongly compete with T and with U, okay? So now that we have this, nice tunability of all the parameters, that they can be tuned more or less independently, one from the other, so we can see the phases that we can observe. So in particular, let's start with this regime where the J-perp is negative and U is 1. So here we work at densities smaller than 1. So no charge gap, the system cannot be an insulator, but we can have a finite spin gap, and this is exactly what we get. So as a function of J-perp, we see that here the spin gap is 0, but here we have a finite spin gap. And the theory of 1D fermions tell us that if we have a regime which has a finite spin gap, this regime can be classified uniquely by looking at two different order parameters. So the first one is the parity operator, which basically captures the fact that you can have fermionic pairing, or importantly, by a string order parameter. So the string order parameter is the order parameter of interaction-induced topological phases, like the Haldane phase. Of course, this is not the case, so we can see that here, this gapped regime is captured by a finite parity, so there should be some fermionic pairing, and we would like to see whether there is some superconductivity, okay? And the answer is yes. So in particular, here we plot the asymptotic value of all the possible correlation functions. So the 3 correlation functions in the first line are related to superconductivity. This is extended singlet superconductivity, so 2 fermions with opposite spin sitting in neighboring sites and tunneling. So this is local singlet superconductivity, so 2 fermions with opposite spin sitting in the same site and tunneling. And this is the triple superconductivity is the antisymmetric solution of the extended singlet superconductivity. And you can see here that the asymptotic value, having the largest value, is the one capturing the extended singlet superconductivity. Okay, so here we can really have a one-dimensional superconductor. Good. So, but I would say that the situation becomes even more intriguing if we flip the sign of J-perp. Okay, here again, we find a region with a finite spin gap. And this region is completely captured by the long-range order of a string order parameter. So which means that we can have some clear indication that we can have a topological phase. But as you know, in topological phases, we should expect the appearance of edge states, okay? And in this case, edge states are captured by a finite expectation value of the magnetization in the system edges. So you can see that here this is clearly finite. And in addition to that, we can also rely on something more, some more theoretical quantity. And I'm talking about the entanglement spectrum. So the entanglement spectrum is nothing else than the eigenvalues of the reduced density matrix. And the theory tells us that as soon as we have even degeneracy of the entanglement spectrum, so we are in presence of an SPT phase, of a symmetry-protected topological phase. And here we plot these lambdas are the eigenvalues, so the entanglement spectrum. And in particular, if you have even degeneracy, this means that lambda 1 is equal to lambda 2, and lambda 3 is equal to lambda 4. So basically, when this psi guy is 0, we have this even degeneracy, which is exactly the case here. So we have all the ingredients to claim that here we have a topological phase. The charge gap, as I told you, is 0, so which means that this is not a topological insulator. It can be a topological metal or liquid, as you want to call it, or it can be a topological superconductor, okay? So in this case, the correlation dominating the system is the one capturing the spin ordering, so it's not related to superconductivity, okay? So this is just, we call it a topological liquid. Good, so this is something already beyond what people can do with Fermi-Hubbard, usual Fermi-Hubbard realizations. But here, we can do even something more interesting, I would say. In particular, we can exploit the full tunability of U. So, and if we move to the regime where U is slightly attractive, so this is what we get. There are two phases. Both of them have a finite spin gap. In between, there is a kind of second-order phase transition. Now, this blue region is captured by the parity operator, while this orange region, again, is captured by the long range of the string correlation function. And this, again, is a topological phase. So we have a finite X magnetization and even the degeneracy of the entanglement spectrum. But here, crucially, so you can see that the correlation dominating the dynamics of the system is the one related to triplet superconductivity. So you can see it also here. This is the decay, the explicit decay of this triplet superconducting correlation function. So which means that here, superconductivity is able to coexist with topological order. And this is a nice example of a one-dimensional topological superconductor, okay? So now there are two things that I want to underline. So the first thing is that, okay, this is our phase diagram as a function of J perp and U. So these blue phases are superconductors, so different superconductors, while these orange regions here, this is a topological liquid, and this is the topological superconducting phase that we can have. Now, if we work in the regime where the on-site interaction is infinite, for example, is a regime that you can have with polar molecules, topology completely disappears. So the fact that we can have these topological phases, these topological superconducting phases, is completely due to the fact that we have tunability of the on-site interaction, okay? So this makes our platform quite unique, I would say. And the second thing that I want to remark is that these topological phases are, very much stable with respect to different densities and different strength of the on-site interaction. So which means that if one day some of you would like to do some experiments, so you don't have to do any fine-tuning, okay? So these regions are quite large and quite stable. Now, all the results that I've been showing you have been obtained at 0 temperature. And and if you want to compare theory with experiments, also, of course, in experiments you have finite temperature, clearly. But if you want to explore phases with a finite gap, and your temperatures are smaller than the gap, in this case, your 0 temperature approximation is usually a very good approximation. But the thing is the following. As I told at the beginning, in one-dimensional fermionic systems, so we have to consider two different degrees of freedom. So charge and spin degrees of freedom. And because of the phenomena of spin-charge separation, we can have that these two gaps can have a very different amplitude. Now, the question is the following. What if we have a temperature able to destroy one of the two gaps, but not large enough to overcome the effect of a finite gap at higher energies? And in order to try to understand this point, we can still use matrix product state. So finite temperature matrix product state, this is quite good, because at least we can go beyond the usual finite temperature mean field treatments, where quantum fluctuations are basically neglected. And quantum fluctuations in 1D are usually quite important. And in order to to explore these phenomena, so this is the model that we derived. So basically, again, we want to consider fermionic magnetic atoms trapped in this two legs system, where we have the tunneling, in the horizontal direction, but not tunneling along the vertical direction. Then the polar interaction is long range, clearly, so we have to consider the repulsion when two particles are sitting in the same rank, then horizontal interaction, and as well diagonal interactions, okay? Good, so in particular here we fix our parameters, so at density 0.5, and these are the values that we can have of J perp and U. But we can clearly also relax these conditions, but we can reach this condition by simply changing the orientation of the dipoles, okay? So if you do that, so what you can see here is that as soon as we switch on J diagonal, so there is immediately the opening of both spin and charge gap, okay? And in particular here, the spin gap is higher than the charge gap. So here, what I can tell you can also have a look to this figure, so is that the gapped spin degrees of freedom are captured by, again, a long-range order of a string correlation function. But crucially, since we have also a finite charge gap, so these finite charge excitations are captured by the long-range order of the parity correlation function. And when we have the combination of these two guys, so it means that there is local order. So there is not any topology, at least at 0 temperature, and this is the configuration that you have in an effective antiferromagnetic phase. And that's why we also have long-range order of these 2-point correlation functions. So SZ, SZ, this is a picture of the phase that you have, where, as I told you, both gaps are finite. And now we can work at finite temperature, okay? So at 0 temperature, we are in antiferromagnetic phase, so we should expect that the staggered magnetization is finite, and this is exactly what we get. Then we increase the temperature, and at some point, the local order disappears, okay? So good, you can say, okay, quite boring. So I inject thermal fluctuations in my system, and at some point, these thermal fluctuations will destroy the local order. But maybe this is not the end of the story. Here we plot again the degeneracy of the entanglement spectrum. So you can see that when the local order disappears, so there is a quite large window in temperature where the entanglement spectrum is even degenerate, okay? So maybe this is again a signature of the fact that you can have a topological phase. So in topological phase, as I told you at the beginning, we should expect finite edge magnetization that we have, okay? So we have some indications of the fact that we can have a temperature-induced topological phase here. But in order to be sure, let's again rely on the behavior, on the decay of the correlation functions. So at 0 temperature, we have long-range order of the string related to the spin sector, the parity related to the charge sector, and the 2 points SZ correlation function. So as I told you in the first slide, so then if we increase the temperature, supposing that we are here, again, we have local order, and again, we have long-range order of all these 3 correlation functions. But crucially, when we are here, we have even the degeneracy of the entanglement spectrum. So, and if we have a topological phase, we should expect to have long-range order unically of the string correlation function. And this is exactly what we get. So the string correlation functions is long-range, while the 2 correlation functions, the other 2 correlation functions decay. So which means that we have all the ingredients now to claim that we have a topological phase, not induced only by the interactions, as usual, but here induced by temperature, by finite temperature physics. And finally, so when we increase a bit more the temperature, we end up here, and here thermal fluctuations are so strong that we enter in a completely disordered phase where all the correlation functions decay. So now I can show you the phase diagram here. This red region here is the one where we find a topological phase. So again, this phase is not an insulator, because the charge excitations are gapless once we cross this line, this window. So it's a topological conductor. It's not a superconductor, so we are working on that. So if you can induce new terms in the Hamiltonian to make it also this one a superconductor. But at the moment, this is just an SPT conducting phases. But what I want to tell you is that, okay, so in this way, so we can prove that also temperature can be, in this, at least in this setting, a nice tool to engineer SPT phases. And with this, I think that I have to conclude. So I hope that I convinced you that, with magnetic atoms in optical lattice, we can have very versatile and at the same time important TJ models. So we had, a quite realistic platform to engineer topological superconductivity in 1D, which is something relevant, I would say. And also, I show you our preliminary results related to temperature-induced topological phases. These are the, what we would like to do in the future. And let me just thank the people involved. So the group of Francesca Ferlaini in Innsbruck and our group in Turin, especially Nitya, who did, all the simulations. And, in this, I thank you for your attention.
Thank you, Luca, so much. Interesting presentation and perfect timing. We have time for questions. Do we have from, okay, Marco Diliberto.
Hi, Luca. Nice talk. Just a curiosity. About classification at finite temperature, is there anything one can say or that has been done?
Yes, so not related to finite temperature, but related to mixed state, which is equivalent, no? Because you know that as soon as you inject temperature, you have a mixed state. The situation is not so clear, okay? In particular, so there are results showing you that string correlation functions in the thermodynamic limit are not really long range, okay? So, but it depends on the symmetry of your system that you have. And in addition to that, so since we want to relate our results to experiments, so we know that the experiments, we had already had 2 experiments, detecting topology, obviously at finite temperature, by using string correlation functions. So for any practical purposes, I would say that our description is fair, okay? But formally, there are open questions.
Okay, any more questions? Okay, Jakub.
Cool, but the thing is the following. These are interaction-induced topological phases. So there is no edge bulk correspondence. So topological invariants are not even properly defined in this case. That's why we just use string. Yes, but so since we are in 1D, we are lucky enough that we can rely on the behavior of string correlation functions and entanglement spectrum.
Okay.
So,
Okay, Odette.
exactly. Yeah. We just follow
Please
the
use the
ground
mic.
state.
Thanks,
We
yeah.
just follow the ground state. So basically, in our procedure, what we do is that we start with an infinite temperature MPS,
Yeah.
and then we, in imaginary time, adiabatically decrease the temperature. So we just follow the, in this sense,
But so now you're saying that you have topology by being, 0.9% the ground state and 0.1% the first excited, let's say.
can be.
So
We
it's a
cannot
mix. It's a
quantify that.
mixture in that
Yes,
sense,
yes.
right? And so, what of the statistical mixture of the 0.1? Okay.
I don't know. So within this formalism, I think that it cannot be, so your questions cannot be answered, because this would imply to do multi-targeting states, which in DMRG, you can target few states, but not so many. And if you're at finite temperature, clearly you need to target many, many states. So I would say this is not within reach with our formalism.
Okay. Thanks.
Okay, Konrad.
Very nice results, Luca. Really enjoyed it. Are all these states adiabatically connected to trivial states, such that I can prepare them in experiment starting from a product state or something like that?
We are at finite size,
Yeah.
okay? So this shouldn't be a big issue, no? Because at finite size you can do any adiabatic evolution. So the problem related to these phases is that they are degenerate. And you cannot cross adiabatically, so you cannot move from a single state to a degenerate state adiabatically. So we need to break the degeneracy, for example, by applying anti-parallel fields at the edge of the system, just to select one of the 2 topological states.
Okay.
And then you do a finite size extrapolation, by sending these fields to 0, and then you see that everything is more or less stable, and you're happy.
Nice.
And number of particles in this model is conserved.
Is conserved. Okay, formally, when you start from infinite temperature, it's not formally conserved, so you need to play a bit with chemical potential to fix the density that you like. But, in principle, you can also conserve the number of particles. This would be very important, for example, if you want to do the same thing for bosonic systems, because we know that bosonic SPT phases should be protected by the U1 symmetry. Okay, so the conservation of the number of particles, while with fermions, this is not an issue.
Any more questions? Okay, because it seems that in comparison with this glorious Kitaev chain model, now it's a significant step forward.
Thanks. We have to be careful, no? So in Kitaev chain, it is known that you can have Majorana fermions. That would be the main goal, but we cannot do any claim about Majorana fermions in our system. And on top of that, we don't have through long-range order of superconducting correlations. So we can have Majorana fermions, but at the same time, I wouldn't bet on that, okay? Let's put it this way.
Let's be careful. So thank once again for the speaker.